Thank you very much for joining us today. My name is Amdemichael. I'm a postdoc at the University of Oxford. Today I'm going to present you two contributions from our group, which is on pre-eruptive magmatic conditions in a geothermal active volcanic system of the Main Ethiopian Rift. So a lot of people contributed to these works, which is listed in here. Most volcanoes are located close to plate margins, so which is indicated by green lines. In these places, plates move apart, becomes close to each other, and move past to each other by creating a good condition for melting and rise of the magma to the Earth's surface for volcanoes. When we see focus on East Africa, there is a prominent structure called the East Africa Rift system, which is formed by 4 to 6 millimeters stretching of Danubian and Somalian plate. In the south, it's characterized by faulting, but in the north, in Kenya and Ethiopia, magmatism plus faulting accommodates the stretching. The Main Ethiopian Rift links the Kenyan Rift and the Upper Rift, and is mainly demarcated by major faults bordering the plateaus to the rift floor. In the actual zone, more frequent faulting and also major caldera hosting volcanoes are systematically spaced. The Borabaricha-Tolmoye volcanic system, which is located in the area at which the rift shifts from north west to more northeast trend of the rift, and which is the focus of our study. Why we are focusing on this? Because it experienced a lot of eruption in the Holocene time, and most of the Holocene products are seated on Pleistocene older rock units, which are exposed in the escarpment. And at least 2 caldera forming eruption occurred in the past. And in the post-caldera phase, effusive and explosive eruption emplaced and blankets the volcanic complex. And in historical time, which is in 1900, a minor eruption emplaced Guyana obsidian coulees, which caused a significant societal impact by displacing a tribe which is located in the northern head of the obsidian coulee. Currently, the volcanic complex is experiencing seismicity, episodic ground inflation and deflation, and also a lot of geothermal manifestation like marolic activities. So when we say pre-eruptive magma condition, it is understanding how hot was the magma and how deposed it is, and what is the volatile content of the magma before its eruption. These 3 main parameters are crucial in determining the eruption behavior. Either effusive or explosive are mainly determined by these 3 magma conditions. And also, this volcanic complex is crucial because of its geothermal resource. So understanding this helps us to understand the heat source region of the geothermal system. We collected a lot of representative samples, and the whole rock chemistry indicates that 2 major composition range: basaltic, which is mildly alkaline, and rhyolitic, with a few samples falls in the intermediate range. The rhyolites are alkaline, which includes both komendite and panthelite. So in overall, three magma sources, basaltic, komenditic, and panthelitic, and from their trace element, they are linked by fractional crystallization process. And we apply different thermometry uh, techniques to calculate how hot was the magma, and the results shows 1070 to 1200 degrees Celsius temperature, which is higher than the komendite and the panthelite. And the feldspar liquid thermometry are more reliable, and they shows two bumps which are associated to the temporal variation of the temperature of the magma. And in order to understand the pressure and how deep was the magma, we use cleanopyroxene associated barometers. And the basaltic magmas stored at deeper crystal level, and the silicic magmas are stored at shallow crystal level. And when we combine both the thermometry and barometry works, we can clearly see that the silicic melts are stored in low temperature, shallow level compared to the basaltic magmas. There is already a published magnetology work in this volcanic complex, and showing that at deeper level there is a high conductive zone, which is overlapping with the basaltic melt, and another shallow level high conductive zone, which is overlapping to our silicic melt zone region. And there is also a high conductive zone, which is covering almost spatially distributed in all over part of the volcanic complex, and located at really shallow level up to 2 kilometers, which is the area which is containing high clay content resulting from the hydrothermal alteration. And we formulated really simplified conceptual model indicating that magma is rising from deeper crystal level and going all through to the shallow level and evolving to silicic melt and stored in shallow level before its eruption. The volatile evolution and content work is part of my postdoc, and we consider two volcanoes for this work, Tolomoye and Poset. Tolomoye experienced two eruptions, older and younger Tolomoye. Poset experienced six eruptions in total, at least. The older ones, Poset 6 and Poset 5, are coming from Poset Barrage. Why we only focusing on Poset 6, Poset 5, older Tolomoye and younger Tolomoye premises, because they host this a clinopyroxene, which have inclusion of melt and apatite, because these two are really crucial for our volatile content study. The melt inclusion in glass chemistry indicates that they are rhyolitic and typical comenditic in composition, and their volatile content shows that they contain prominently chlorine and water. So the chlorine content ranges between 0.1 and 0.3 weight%, and the water is ranging between 1 to 4 weight%. But the other fluorine, sulfur, and CO2 are minor in content. When we come to apatite composition, there are two clusters, especially in the magnesium content and also in the rare element content, which is indicating the apatites have, especially the older Tolomoye premises, apatite from the older Tolomoye premises are have different composition in terms of the trace element. This is also similarly indicating the volatile content, showing that the older Tolomoye premises are higher in chlorine content high in water content and lower in fluorine content. But the CO2 and sulfur content is more or less similar. No, there's not much systematic difference. When we come to the volatile evolution, the, it shows a linear trend. So the variation of each spot of analysis is the result of fractional crystallization. And the linear trend indicates the condition is water undersaturated. And we, by using different partition models, we calculated multi-volatile from the apatite chemistry. And the result shows that all the Tolmoyopamids have higher chlorine and water content compared to the others, but lower in fluorine content, which is not clearly suggested on the multi-inclusion study. So the overlap between the apatite and multi-inclusion give us more robust results and more reliable results. So to sum up my talk, transcrystal magma plumbing system is responsible for eruption in the Pora Barrecha volcanic system in the past, where basaltic and paracalorite magmas are stored under distinct pressure and temperature conditions. And the multi-inclusion and apatite studies from Tulumoye and Boset Parecha Permis reveals unique volatile content for some of the eruptions than other considered paracalorite magmas. By saying this, I want to say thank you very much for your attention.
Do we have any clue about residence time of the melt in the magma chambers from geochemistry? Is there any way because you talked about, you show clearly that your data supports a model where we have transcrustal distribution of magmatic chambers, and I'm assuming that these chambers are feeding one another, but there must be some temporal constraints on that, or temporal components to that, or because I would assume that the conduit is not permanently open and the melt just goes through all the time. Is there any constraint from geochemistry on what the residence time might be at deeper depths in the crust versus shallower crustal depths?
Okay, thank you, Paula, for the question. So, first, so trying to understand the time scale is also part of this project, but most of the crystals, because when you are dealing with trying to answer this time scale, you need some kind of zoning pattern in order to see some diffusion pattern to calculate the time scale. But most of the crystals in here, what we are working on, they are homogeneous, so there is no any zoning, so it's difficult to constrain the time scale. But there is one work I was collaborating with. We tried to work on all living crystals because they clearly show some zoning. But the samples are from a different volcanic system that is in the Main Ethiopian Rift.
I see.
But for this, we didn't constrain the time scale because of this issue. Every crystal we were working on was homogeneous, so we didn't do anything on that.
I see. Okay, thank you very much. I think we have a question in the chat. Sarah Stamps, do you want to unmute?
Yeah, sure. I was wondering how unique chlorine is in a volcanic system.
That was a really good question. For the case of the East Africa system, it's not unique. So chlorine is usually dominant in the volatile species. But compared to the subductions, or maybe it can be, there is some content-wise difference. But in overall, in the East Africa Rift system, chlorine is usually present in most of the analysis, so it's not that much unique. But when we do some comparison between the different magma sources, there is like some slight difference in the content of the chlorine. as you see in some of our results in here.